All right, hi, I'm Bill Bain. I'm from Scale Out Software, and I hope you had a nice lunch. I'm here to talk to you today about enabling operational intelligence using Hadoop MapReduce. And so you're probably wondering, what is operational intelligence, or how does that fit into all of the talks we've seen over the last few days, and how does it compare with traditional business intelligence in the data warehouse? So I'll talk about that, and then I'll talk about how we implement operational intelligence using in-memory computing techniques. And you're going to find these techniques are very similar to Spark and Storm, but they're different in some key ways because they're used in live systems, and I'll explain that. And then I'll talk about how we implement Hadoop MapReduce to run unchanged on an in-memory data grid, and then give you some examples in financial services and other areas, e-commerce, and see what questions you might have. So first of all, online systems are systems that typically are holding live data that represent real-world entities. So for example, there might be shopping carts in an e-commerce system, or partially completed trades in a financial trading system, or airline reservations, or they could be set-top boxes for a cable company. So you have in-memory data representing a live system, and this data is being updated continuously through a stream of updates. And the internal system has to then provide feedback. The in-memory system that's hosting this data wants to be able to provide feedback to the live system. Now, people have been using a technique called in-memory data grids for over a decade. You might have heard of products like Oracle Coherence, Infinispan, open source Infinispan, and other products like that, Gemfire and Gigaspaces, and we have products from Scale Out Software as well. And so they've been hosting memory for storage, storing data in memory and scaling that storage capacity for, as I say, for over a decade. And now the ability to do data parallel computation on that data while it's live and changing, and then feed back to the live system, is the opportunity that operational intelligence provides. And here are some examples of that. You can see some examples, for example, in an equity trading system, to make sure that traders are alerted to perform trades as the market prices change during a day. I have a demo of that I'll show towards the end. Other examples would be e-commerce systems providing next best offer to web or online shoppers, or even at point of presence in brick and mortar stores, to provide real-time offers. And we've seen examples of that and other approaches to it in other talks. And this is an approach that's centered around in-memory computing on live mission-critical data. And of course, there are other examples you can think of, like airline reservations. We host airline reservations for one of the major airlines in our grid, and the ability to then be able to reroute passengers when a weather event occurs or equipment failure occurs, that's a very important feature of in-memory computing. And of course, power, inventory, and other examples. So the two big challenges that in-memory systems have in providing operational intelligence are, number one, performing updates fast to keep up with the incoming stream of updates that need to be applied so that the in-memory representation matches that of the real world. And secondarily, to be able to perform analytics fast enough that recommendations can be provided in what, I'll just use the term real time and I'll define it, in real time, meaning I think we heard the term from Yahoo, the human interaction time. So that means milliseconds to seconds. By real time in this context, we don't mean the kind of real time you would see in a flight control system, 10 milliseconds, or in an algorithmic trading system, 1 millisecond or less. We mean real time measured in human interaction time. So hundreds of milliseconds to a few seconds. And that contrasts with batch analytics. Look on the right-hand side of the slide. So traditional Hadoop, that when it emerged several years ago, and of course we know as the technology is progressing very rapidly with Spark and Storm and other technologies like that, that we're moving away from the traditional usage model of Hadoop MapReduce. But if you look on the right-hand side, traditionally we're talking about batch processing of static, very large static data sets, disk-based, so data motion to and from disk, taking minutes to hours. And so when you're analyzing offline petabytes of data, you make a certain set of trade-offs in the execution environment, the scheduling environment, that are quite appropriate because those overheads are lost in the overall computation time. But when you move to the left here to the real-time environment, going from business intelligence to operational intelligence, then you're dealing with live data sets that are typically memory hosted, measured in the hundreds of gigabytes to terabytes, in which you want to be able to respond in hundreds of milliseconds to a few seconds. So it's a different environment. And on the right-hand side, you can think about strategic value from big data analytics, finding strategic insights for an organization. On the left-hand side, you can think of it as providing tactical insights. So if you think about how these might work together, then you can see, let me just go to the slide here. These can work together in an integrated environment in which you have the data warehouse hosting the Hadoop stack, providing the strategic guidance, but receiving data live coming in from points of presence. This is an example that we ran into. We have a blog on this on our website. We ran into with a very large, I'll say a restaurant corporation that has thousands of stores serving food, and they are streaming data directly into their data warehouse continuously, and then the data warehouse is looking at that data offline to figure out things, like which foods are most popular in which regions, which products should they, where should they ship products so that they will get the best return, that sort of thing. But at the point of presence, they're worried about things as how long is it taking to serve a customer. So if you can think about using operational intelligence using Hadoop MapReduce at the periphery, then you get two benefits. One is you can perform the ETL function, which has to be performed in any case to convert the data coming in from the points of presence into the data warehouse, for example, to store it in HDFS. And in addition, provide tactical feedback directly, saying for such things as, that when we're preparing these foods, some foods are taking too long to prepare, customers are unhappy. You can provide some tactical guidance to the point of presence while you're also moving the data upstream to the data warehouse. So these two techniques fit very nicely together. I'll just go back to see. This is just another way of looking at this issue of how in-memory data grids are attacking the problem of operational intelligence using different approaches than are used for offline data warehouse batch analytics. And one of the key things is that batch analytics is really designed for multi-tenancy. We find that in operational environments that single tenancy is a typical usage model because these in-memory data grids are embedded within an operational system performing a single function, but performing it 24/7. They're never offline. So moving forward, this is the architecture for providing operational intelligence using in-memory techniques that we have employed. And what's going to be striking, I think you'll see, is I'll show you a picture of our view, my view, of the Spark architecture, and they're very close. At a high level, the architectures are very similar because at some level they're making the same set of trade-offs. The first one is, of course, we're talking about storing data in memory instead of on disk so that it can so the analysis can proceed very rapidly. But two key differences. One is that we're talking about applying updates to in-memory data so that we can have a rich view of the state of the real-world system. And we can further augment that with data coming from disk. So for example, if we're representing an online shopper as an entity in memory, then the clickstream data could flow in to give the in-memory representation the latest possible data about what that shopper is doing. And then we can pull in the customer's preferences and history from, say, MongoDB, any scalable NoSQL store, for example. And that way, the analytics has all of the data it needs in order to make the best possible recommendation back to that customer. So you see that we're centered around the in-memory state and not around processing the incoming stream as you would with CEP, complex event processing, or STORM, or other techniques which are focused on the stream instead of on the in-memory representation of a real-world system. And there are other implications of this, which we'll get to in just a second. But first, let's talk for a minute about what an in-memory data grid is. We find that some people have used them for years and know all about them, and other people have never heard of them. I had somebody come up to the booth yesterday and said, what does IMDG stand for? So therefore, I will just take a minute to explain to you what they are. First of all, they typically have been deployed at the business logic layer, and they provide a representation of in-memory objects, but they're stored out of process within a grid that's scaled across a cluster of servers. And it's providing two main features or capabilities for the customer. One, it's in-memory storage that spans a cluster of servers, and it also has integrated high availability through data replication, and that's important. This is high availability in case the server fails by keeping a copy of every stored data object on another server so that you can immediately have access to that data if a server goes down. And you can imagine that in an operational environment, you really need this capability of instant high availability because you can't afford to have customer data offline when it needs to be accessed in a live environment. So in-memory data grids are accessing individual data objects in a collection that's, for example, a collection of plain old Java objects or plain old .NET objects that are stored in the grid. And so they're able to do create, read, update, and delete. People talk about CRUD APIs on these objects. Now, to look in a little more detail at this, they look like unstructured collections of a given type. Typically, that's the usage model. So they're collections of a type within one collection in the grid. They're stored as serialized data, but they're accessed very much like they were in-memory collections. In addition, each object has properties that have been added over time. People, as they've been using in-memory data grids, have added attributes to the objects in order to give them richer semantics that are very useful in an operational environment. For example, they have timeouts, so they can disappear automatically. They have access to event handling, so events can be triggered when the state of an object changes. They can be organized in hierarchical relationships, we call dependency relationships, so that you can manage their lifetimes as a collection. They can have distributed locking, whether it be pessimistic or optimistic, transparent access to a backing store, so that if they're missing, their contents can be pulled from a backing store and they can be checkpointed to a backing store. So you see that objects are not just plain old objects, but they're objects with a big bag of extra attributes which are very useful for the processing that's done in live environments. And we're going to see that all of this baggage becomes baggage when you're starting to do MapReduce, and that gives rise to doing some optimizations to implement MapReduce, which we're coming to in a second. So another thing that's very interesting is that in-memory data grids can layer in-memory computing. So they're not providing just in-memory storage, but also providing in-memory computing. We use a technique called parallel method invocation, which is simply an object-oriented implementation of a very well-understood technique from high-performance computing. It derives from the work in the 80s and 90s in parallel supercomputing using message passing. You might have heard of MPI, the message passing interface, which became a very popular way to structure data parallel and task parallel computations on parallel supercomputers. And that can be re-implemented in an object-oriented way, and that's what we've done with what we call parallel method invocation. And you can think of it as executing a set of mappers, which we just call eval, or just running a user-defined method on the set of servers, but they're applying that to a queried set of objects based on their properties. So that's a distinction from MapReduce. So you can subset the objects on which you want, or key value pairs, think of it that way, on which you're processing these eval function. And then there's another feature that we have built, which is global aggregation, which in the old days with MPI was done with message passing, but it can be done in an object-oriented way so that you end up with one resulting result object that can be given back to the user. And that can be done in logarithmic time if it's done with a binary tree, combining tree. You can think of global aggregation or global merging as combining. And if you think of having one reducer that does the same method as a combiner, then this technique is essentially doing running the mappers and then just doing global combining. But this is the platform on which we can build MapReduce. So it gives us very fast startup time because it's inline scheduled. It also has a built-in global barrier so that it can be synchronized, so we can synchronize the map and reduce phases. And we also have the opportunity here to automatically ship code and bring up the execution environment so that it can be very simple from the user's point of view. Now, what's interesting is that this technique, and any data parallel technique that does not move data across the servers, as MapReduce has that property as well, that it avoids data motion for the map phase, can eliminate data motion and thereby give you scalable throughput. And scalable throughput means as you add workload, add more work to do, and add servers to handle that workload, you should see a linear increase in throughput. And that is in fact what we have measured running a financial services computation. This was a backtesting algorithm we ran on a set of stock histories. And you can see that if you randomly access objects from the grid, then the scalable throughput falls off very quickly. And the reason for that is the network becomes the bottleneck, right? So as you move more and more data across the network, that becomes the bottleneck to scalability. And that's why in, I'll say, the old days of the 80s and 90s, we had fairly exotic networks, mesh routing, torus routing networks, in order to keep the bandwidth scalable as the number of servers was added. people have moved to commodity networks because they're relatively fast, but you still can get into this problem, and therefore you need to avoid data motion. And that is in fact what you get with in-memory computing when you use data parallel computation that accesses data that's only local to that server. Where you do get data motion in any data parallel computation, of course, is in the shuffle stage of MapReduce, and then finally after the reduction and combining the data or retrieving it from the output of the reducers to bring it out to the system that needs to make use of it. So this is a comparison to Spark, and with apologies to the next speaker, who is a Spark expert. I'm not sure if he's in the room right now, and anybody else who's an expert on Spark, because I'm not, okay? But I want to just give you sort of a high-level view of how we separate the two. We view Spark as being a technique that was designed to accelerate data parallel analytics, and it provides some very powerful features such as resilient distributed data sets and the Scala parallel operators. It was not designed, to my knowledge, to fit into a live operational environment. So there are two aspects of Spark that distinguish it from the use that I'm describing of an in-memory data grid with data parallel computation layered on top of it. The first aspect is that that RDDs, I'll just say RDDs, do not do CRUD. So they're not designed to update individual entities within the RDD. And you can see in a live environment, if you're hosting a collection of shopping carts, you want to be able to add and remove items from each shopping cart. Or if it's financial portfolios, you want to be able to add trades, remove trades to the portfolios, while at the same time you're doing data parallel analytics. So instead of just focusing on the data parallel analytics, the operational intelligence system has to do both live updating and the parallel analytics at the same time on the same data. So you can see it's a different set of trade-offs. Now the second thing, this slide says lacks high availability towards the bottom. The key observation there, the word lack is not the right word. I went back and reread some of the early research papers yesterday, it's quite intentional and quite purposeful, and it makes a lot of sense if your focus is on doing very fast, highly accelerated parallel analytics, whether it be MapReduce or any of the other number of things that we've seen that Spark can do. It was a choice to use Lineage, which is a fault tolerance mechanism with a smaller footprint, if you will, than high availability through data replication. But for live environments, our customers need high availability, meaning that the data can be accessible within a second or two after a failure, as opposed to having to reconstruct that data by perhaps rerunning operators that ran in the past, or having to cache all the intermediate steps, or whatever is required. And I'm not an expert on how Lineage is implemented in Spark, but it's a different approach, and it was purposefully made in order to reduce the overhead of supporting fault tolerance, but yet provide it so that if you needed it, it was there. So this is how we implement MapReduce using an in-memory data grid. We do it in two phases of what I was describing as parallel method invocation. In the first stage, we run the mappers as one parallel invocation. And then they, of course, since we're running standard MapReduce or standard mappers, we can input data into the mappers from HDFS or any data source for which there's an input format. And likewise, we can input data from the grid itself. And that's the usage model we're most interested in. And then the data is shuffled through the grid and stored in the grid, and then consumed by the reducers, which run as a second phase of parallel method invocation. So it's interesting, when I was trying to figure this out, I was trying to say, well, how is parallel method invocation different than MapReduce? And it turns out that it's neither a subset nor a superset. It's a subset in the sense that MapReduce runs as two phases of PMI. But it's not a subset in the sense that it can perform global merging, which is not something that's available directly in MapReduce. So the output can, of course, flow to HDFS, or it can flow to the grid. And that data that's being ingested and being output can be live data. And distributed locking can be used to ensure synchronization if necessary. So that's how we implement MapReduce on an in-memory data grid using a lower level, if you will, platform. So this is, it's analogous to using TES to implement MapReduce, but of course I'm not going to compare this to TES. I'm just saying that, if people have worked on building more streamlined platforms on which to host data parallel operators, Spark has one, there's TES, and then and this is another. This one is tuned for a live environment. And that's what distinguishes it from some of the other technologies we've seen. Now, in order to run an application, It's interesting, the yellow highlighting is missing, but you'll see if you look at the job object here, what we did is we subclassed the job object. That's the only change to a standard MapReduce application. So without Yarn, you do have to make a change, and that's the change, to subclass the job object. The rest of the code is unchanged. So our goal here is to absolutely avoid any vendor APIs in implementing MapReduce. Just make it work, and make it work without code changes. That way the skill sets could be leveraged. So I say we, it's actually this gentleman here, Michael Sobolev, for the recording, who implemented this technique of subclassing the job object. Now, with Yarn, we were able to determine that all we have to do is change the MapReduce execution engine so that Yarn gives us control to run within the grid. And so, therefore, no code changes are needed whatsoever. And you can see there's a really nice integration between the use of an in-memory data grid and the use of a standard Hadoop platform, because you can use the in-memory data grid's MapReduce engine as an alternative for operational data and use the standard MapReduce execution engine for batch data and offline data. And also, you can see data can be ingested with either engine from HDFS, and then, of course, the in-memory MapReduce engine can ingest data from the grid itself, as well as updating that data live. So that's a key differentiator, that the arrow coming in from the left shows you can access data from incoming streaming data can be accessed and stored in the grid, as I mentioned earlier, so that you're working with live data in the grid. So one of the little experiments we did was to run Hive on top of, unchanged, on top of this execution engine. So this execution engine can run Hive using Yarn. Because Yarn allows us to redirect control, we were able to run Hive unchanged. Now, we weren't able to get the kinds of speedups we were looking for yet, and we attribute that to several reasons. One thing we had to do, which is I don't think affects the speed, is we learned that Hive's implementation is not thread safe. So we had to implement multiple JVMs to support Hive, but we were able to get this 3x speed up, and mainly we're able to do queries now on in-memory data, not just on data in HDFS. So that was a primary goal. But I think part of it is if we did not want to do a Hive distribution. We don't want to be in that business of providing distributions to the community, so that running unchanged means we couldn't employ some optimizations that you would find in say, Shark or other implementations, which can dive into the implementation and optimize it. So that's one aspect of it. The other is we tuned our implementation of the shuffling. I'll tell you a little more about that in a few minutes, but ours is tuned for multi-valued keys. And so our experience so far is that we're not seeing a lot of multi-valued keys with the Hive queries we're doing. And so our implementation was, there's a spectrum of optimizations one could apply. You know, you can think of the design space as single or multi-valued keys, and so forth. And so we really optimized for multi-valued keys, and therefore I think that may be contributing to not getting a 10x or higher speed up. Now, this is the execution cycle of running MapReduce within an in-memory data grid. The first thing to point out, and I think people, even at this point in the talk, will be confused, that we do not require a Hadoop distribution. So you can just run this standalone, but typically you might want to access HDFS, in which case you would just install the grid on the same cluster as Hadoop is installed, and that way you can access HDFS and you minimize network transfers in order to do so. It's not necessary to run on the same cluster, but it's a typical usage. But almost all of our customers run in their own standalone on-premise environments that don't have Hadoop installed, because they're accessing data from the grid itself. So what happens is when you run the application from the remote workstation, then the client libraries will spin up a set of JVMs or .NET runtimes if you're running C#, and they can be persisted to run across multiple MapReduce jobs, and thereby further drive down the scheduling time. And that's automatically handled in the code. The jars are automatically sent out, and the job runs. And then if you decide to use the global combining, the results can be sent all the way back to the workstation. Now, this shows you how you would accelerate the startup times by simply creating an invocation grid, and we've enhanced the job objects so that you can just specify the invocation grid and then use it over and over again. This is identical to what Spark does, right? They just keep data in memory. There is only one invocation grid, right? So we allow multiple invocation grids for multi-tenancy support, but the point is that they can be persisted across multiple jobs, and that's typically what's done. They're brought up and left running all day. They're never brought down. Now, to access in-memory data, we've provided an input format and output format, and the real challenge is to manage large sets, large volumes of small key value pairs, and to push them into the mappers in a highly pipelined way and push them back into memory in an equally efficient way. So one of the things we learned, and I mentioned earlier about how we've enriched all the objects and stored in a grid with all of these advanced features like property-based query and distributed locking. And so it was pretty obvious if you're going to run MapReduce programs that have a very large population of very small key value pairs, then you need to have a storage model that fits that. So we created a new storage model based around the Java name map, and that's the one that we use primarily for MapReduce. And what's different than most implementations is that these key value pairs in memory can be individually accessed and updated so they can store live data, and yet they can be efficiently managed as if they came from HDFS and pipeline into the mappers and out from the reducers. So this is a new storage model that's designed specifically to support MapReduce. We also use the name map transparently to store the shuffled data between the mappers and the reducers, so that as data flows between the two, it's stored using the same optimizations in memory in the grid. So here are some of the optimizations that a name map performs. First of all, it's storing key value pairs in chunks. And let me just explain that key value pairs that we're trying to support here might be as small as 10 bytes or 100 bytes. Whereas typically, if you look at the history of in-memory data grids, objects have been in the range of thousands of bytes to hundreds of thousands, sometimes megabytes. And that's why they can afford to have these rich attributes that I described. Whereas most people thinking about doing MapReduce are thinking about very lightweight small objects. And so that's why we needed to create the name map abstraction and implement that in the grid. So the other thing is we can use the chunking mechanism to create automatically splits and partitions for MapReduce. And that way all of that can be automated and handled very efficiently by the name map itself. And also we can pipeline, as I mentioned, the chunks into and out of the mappers and through the grid for the reducers, and then from the reducers back to the grid. And this all can be done by using this one mechanism that's leveraged in all three places: input, intermediate, and output, and also for batch updates to the name map itself. So we can do bulk updates and bulk reads, and that can all be done using the same technique. And also, the techniques we're employing here allow you to turn off sorting, and I'll say a little bit more about that in a minute. Now, another thing that's very interesting to do is to leverage this same technique to cache HDFS data as key value pairs. And that's something we've implemented so you can wrap your favorite input format with an input format called the dataset input format. And then what we'll do is I'll go to the next slide, we watch the key value pairs flow into the mappers and then cache that whole dataset in the grid if it fits. And if it only partially fits, then only part of it is served from the grid and the rest is served from HDFS. And as a result, you can dramatically speed up access to HDFS when you do the same job multiple times on a given data set. And pipelining of the chunks is used to both the record phase to store the data in the grid, and then what we call the playback phase to move the data into the mappers. And because it's key value pairs and not HDFS records, then you're avoiding having to reparse those records to create the key value pairs. So the performance we're seeing from this implementation of MapReduce using an in-memory data grid is showing that the startup times are just a few milliseconds, if that. And we measured 20x about a year ago speed up on word count, which we just thought we needed some well-understood benchmark just to give people an idea of the difference. But on the real-world examples that we have been implementing, we're getting much closer to 40x speed up, and we're now pushing 50x on a financial services demonstration that we've created. And I'll show you a video of that in just a minute. And so we've added several optimizations to this implementation. One is this optional sorting, so you can turn off sorting if you don't need it. Another is that we've added the ability to pass parameters to the mappers, and we multicast that out. So we multicast the startup of the mappers. That means we're doing it in logarithmic time because of the fact that we use a binary tree to implement software multicast. And we also have global combining, so that if you want, you can collect all of the results and send them back, and without having to go to HDFS or to the grid and individually pick up the results of the reducers in order to combine them globally. So those are two optimizations we've added in addition to what I mentioned before, the HDFS caching. The two primary limitations are the fact that intermediate data has to be kept in memory, and although you can have terabyte and larger size grids. And the second limitation, of course, is that there's no specific support for security and multi-tenancy, and we're seeing that this is becoming a really big issue. So in-memory MapReduce, using an in-memory data grid that manages live data, now allows MapReduce to be applied to operational environments to work on live data without having to learn new skill sets, use vendor-specific APIs, just to do standard MapReduce and apply that to live, fast-changing data. And by making a set of optimizations and trade-offs to fit the live environment, we're able to drive the time it takes to do a MapReduce down to hundreds of milliseconds for a typical application, and avoid the use of vendor-specific APIs. So this is an example I'll show you, and then I'll show a video in just a minute of this. So let me just run through this real quick. So this is an example of a hedge fund managing a set of vertical markets, hedging strategies, and its goal is to alert traders when they need to make trades. And they were storing all of this data in a big database, and once every 15 minutes doing a whole bunch of queries, updating their view of their strategies, and then deciding what trades to make. And they needed to be able to do this within seconds. So we applied MapReduce to this problem, but again, this is an operational problem, so this is not something that you would do with the standard approach. So what we did instead is we stored these hedging strategies as objects in the grid, as a collection of objects. So you would think of all of these strategy objects as being one collection, or if you will, one RDD if it were Spark. Now, within each object, you have a set of long positions and short positions which have to be kept in balance. And when a market feed comes in real time, that will upset the balance, and at some point, some strategy needs a trade. Also, there are business rules that are unique for each vertical strategy. So when you do MapReduce, the mappers have to not only rebalance, they have to check the balance, they also have to apply the unique business rules to see, does a trade need to be made, and if so, generate an alert. And then you have to globally collect all those alerts and send them back to the trading desk. So the two things, the two extensions that I mentioned, we use here with our MapReduce implementation. One is we chose to take market snapshots every second and then simply multicast them out to the mappers. And so the mappers would run, and they also, those mappers, and then updating the data in the grid. So part of what they're doing is not just analyzing the data, it's updating the data in the grid. Then they analyze the business rules, and they optionally generate an alert. Now, instead of having the alerts flow out to the grid and have to be collected as the output of a set of reducers, we simply use the global combining, and we skip the reduce step, and we globally combine into one object all of the alerts, and then feed them out to a display like this. So this display, this is just a mock-up we've done as a proof of concept. It's not a production UI. So on the left-hand side, well, actually, I think we can go to the video now, and I'll show it to you in the video. So on the left-hand side are a set of strategies that represent about 2,000 strategies that they're maintaining. They could go up to hundreds of thousands of strategies. And then we alert them. The alerts are represented by the yellow highlights that show you the strategies that are out of balance and need trading. And then when the trader clicks on a strategy, the trader sees what you see on the right. And so first of all, you see the set of positions, and then you see their prices, and you can see their prices changing in real time as MapReduce runs continuously to update the pricing and look at the allocations to see whether they're matching the target or are out of balance. And when they're out of balance, then a stock is alerted and is highlighted on the right-hand side. So each one of those green bars moving to the right represents one MapReduce, and they're taking about 300 milliseconds. So you see there's a highlighted stock there. And if you look on the upper left, you can see the time if you can read it. And measure, I think it's about 250, 300 milliseconds. On the bottom, that's a standard Apache distribution. I'm embarrassed to say at this august conference is 1.2. But anyway, it's, that shows you that that was running in about 15 seconds. And so we were getting about a 40x speed up over standard MapReduce. So the net result is these traders get these alerts within milliseconds, and this could be plugged into an automated trading system. So if it met certain criteria, then they would just immediately trade. And we've done the video. This is just a quick example, and then I'm going to wrap up to show you that how you can run a grid on a terabyte of data. We ran this on Amazon. We wouldn't need 75 servers today. This was run last year. But the point is that this data is being updated at the rate of 1.1 gigabytes per second. And that's the distinction, is the data in the grid is being analyzed with MapReduce. We're doing a stock backtesting algorithm at the same time that it's being updated. And the net effect is you can do a MapReduce in 4.1 seconds. And that's the bottom line there that's highlighted. The upper line represents no updates, so you can see the impact of updating on throughput. But in both cases, you get a linear scalability, and it's running very, very quickly. This is a quick example in inventory management, and it shows you again how we're focused on the in-memory representation of the real-world state and not just the state changes. So we have, this company is a big online retailer of perishable goods, and you have orders flowing in and perishable good inventory changes flowing in, and they kept those siloed in 2 different systems. And the goal is to, how do you reconcile that faster, instead of reconciling it once a day as they were doing, how do you reconcile it within minutes or seconds so that you can avoid completing orders for goods that are either damaged or didn't arrive in time or have perished. So what we're able to do is show them, well, what you do is you store a collection of SKU objects representing each product, and then apply the updates to the SKUs, and then run your reconciliation algorithm, which is highly proprietary to them, on the SKU objects. So you see it's a data parallel computation that can be implemented as MapReduce, and it's working on an in-memory representation using live data that's changing rapidly. It has to be highly available. So I'm going to skip the other examples. This is a recommendation engine. I think we need to have time for questions. Another example in telecommunications, cable systems. And just to recap, what we're doing here is implementing operational intelligence using in-memory computing for systems that are managing live data in memory. So we're extending in-memory computing not to just do storage, but to do in-memory computing using data parallel computation models. We find a lot of people, probably not in this conference, but a lot of people that we talk to, potential customers, confused MapReduce's batch implementation with the design pattern. And the design pattern is perfectly suitable to real-time use, as I'm sure you all know, but the batch implementation needs to be replaced with a real-time implementation, as we've described here, so that you can get results in hundreds of milliseconds to seconds, so that you can impact the operations and enhance the performance and the productivity of an operational system. So in so doing, you leverage all of the Hadoop skill sets we have and yet get the benefits in this operational environment. So thank you very much, and are there any questions? I don't see any questions. Okay, well, thank you very much.